Good morning. Today we are working on day 13 of Advent of Code, which I realize today is the 14th of December, and I'm behind today, so I'm going to try to get caught up by doing two. So yeah, we'll just go ahead and jump in here. Day 13, Claw Contraption. Next up, the lobby of a resort on a tropical island. The historians take a moment to admire the hexagonal floor tiles before spreading out. Fortunately, it looks like the resort has a new arcade. Maybe you can win some prizes from the claw machines. Claw machines here are a little unusual. Instead of a joystick or directional buttons to control the claw, these machines have two buttons, labeled A and B. Worse, you can't just put in a token and play it. It costs 3 tokens to push the A button and 1 token to push the B button. With a little experimentation, you figure out that each machine's buttons are configured to move the claw a specific amount to the right along the x-axis, and a specific amount forward along the y-axis each time that button is pressed. Each machine contains one prize. To win the prize, the claw must be positioned exactly above the prize on both the x and y axis. You wonder, what is the smallest number of tokens you would have to spend to win as many prizes as possible? You assemble a list of every machine's button behavior and prize location. This is your puzzle input. For example, blah. This list describes the button configuration and prize location of 4 different claw machines. For now, consider just the first claw machine in the list. Pushing the machine's A button would move the claw 94 units along the x-axis and 34 units along the y-axis. Pushing the B button would move the claw 22 units along the y-axis and 67 units along the 22 units along the x-axis and 67 units along the y-axis. The prize is located at x equals 8400 and y equals 5400. This means that from the claw's initial position, it would need to move exactly 84 units along the x-axis and exactly 54 units along the y-axis to be perfectly aligned with the prize in this machine. The cheapest way to win the prize is by pushing the A button 80 times and the B button 40 times. This would line up the claw along the x-axis and the y-axis. Doing this would cost 80 times 3 tokens for the A presses and 40 times 1 for the B presses. A total of 280. 3 times 80 is 240 plus, okay. For the second and fourth claw machines, there's no combination of A and B presses that will ever win a prize. For the third claw machine, the cheapest way to win the prize is by pushing the A button 38 times and the B button 86 times. Doing this would cost a total of 200 tokens. So the most prizes you could possibly win is 2. The minimum tokens you would have to spend to win both prizes, is 480. You estimate that each button would need to be pressed no more than 100 times to win a prize. How else would someone be expected to play? Figure out how to win as many prizes as possible. What is the fewest tokens you would have to spend to win all possible prizes? I think the hardest part about this is actually going to be parsing this. Probably can use some regex to do it. But yeah, that's probably the most difficult part. Because all that we're really doing is we're really solving, well, I mean, you don't have to do this with math. You could do this with loops and do it iteratively. you start at 0, you press the buttons, you increment X and Y, you check if they equal the location of the prize, and then you just keep doing that. And if at any point you exceed 100 button presses, or if at any point you exceed the X and the Y of the prize, then you can't get there. However, this is just math. So how can I? So let's just open Notepad really quick. Actually, we can do this in the comments in the code. So this first one, if we just look at this first machine, right? This first machine is basically 2 equations, right? So we have this equation, and we have this equation. No, we have this equation, and we have this equation. So what this looks like, if we were back in like algebra, is we're basically trying to solve this. So 94A plus would it be? Yeah, it'd be 94. So you can think of it as 94 times the number of times you press A. So 94 times A plus, let me add some comments. 94A plus 34, plus 22A equals 8,400, right? Because every time you press A, and then every time you press B, and you've got to press those X number of times to get you to 8,400. So that's actually going to be B. So the number of times you press A times 94, the number of times you press B times 22 should equal 8,400. And then your second equation is 34A plus 67B equals 5,400. So this is moving X. This is moving Y. And so I don't know how many people will remember this, but this is just algebra. This is just systems of equations, and there's two ways you can solve this type of equation, or this type of systems of equation. You can do it through elimination, or you can do it by substitution. And so if you do it by substitution, that basically means you take one of your formulas and you would convert it to be equal to the value that you want to substitute for, right? So let's say I want to substitute for A. Then I would take this equation down here, and I would get all my terms on one side so that I could say A equals this thing, right? So what that would look like is we could subtract both sides by 67B, and then we could divide by 34A. No, divide by 34. So we could say, we could essentially turn the bottom equation into something like this that says A equals 5,400 minus 67B divided by 34, right? And then you could simplify that further. But then in order to calculate what B is equal to, you would substitute that back into the top equation, right? So then you'd have something like 94, 5,400 minus 67B divided by 34 plus 22B equals 8400. So now you just have one term, which is b, that you're solving for, and you can do all your normal, algebraic things to get you to b. That though is a little complex, I feel like, for this would be, I feel like this approach, doing it through substitution, would be more complex. There's another approach we can use that will use, it's not substitution, I think it's called elimination, where basically normally what you do is you try to find the greatest common denominator of the terms in the equations and then multiply them, right? So basically what you need to do is you need to get these equations to a point where you can eliminate one of the terms by subtracting one from the other. So what do I mean by that? I mean, right now, if you subtract this equation from this equation, you're not going to be able to eliminate any term at the moment, right? 34 doesn't cancel out 94, 67 doesn't cancel out 92. So what you need to do is you need to multiply each equation by a factor, the whole equation by a factor that does allow you to do that elimination of one of your terms. So instead of worrying about finding the greatest common, I think it's called the greatest it's either the greatest common denominator or the greatest common factor. Instead of worrying about doing that map, what we can do is we can just actually just use this leading value for a in each equation and use that to multiply by the other. So what do I mean by that? So if we do this, if we say 94a plus 22b equals 8400, and we multiply that by 34, and then we do the same thing below here, where we say 34a plus 67b equals 5400 times not 34 but 94. Then what's going to happen is we're going to have the ability to have a term that we can eliminate, which is going to be the a term. We can just get rid of it. So what we'll have after we do that multiplication, right, and so we can say 94 times 34 equals 3196a plus 22 times 34, that's 748b, and that will be equal to 8400 times 34 equals this, 28560. And then our bottom equation becomes 3196a, because again, we're multiplying 94 by 34 on the bottom, and on the top, we're multiplying 94 by 34, right? So they're the same value. And then this will be 67 times 94. Yeah, that's right. 66298 b, and that will be equal to 5400 times 7 0. I'm actually going to put this bottom equation on top of that. And then now what we can do is we can actually subtract these, right? So we can subtract this equation from that equation, which means what we're left over with is 6 to 9, 8, minus 7, 4, 8, which gives us 5, 5, 5, 0. B equals 5, 0, 7, 6, 0, 0, minus 2, 8, 5, 6, 0, 0, 2, 2, 2. And then we just solve for B, right? So we say B equals 2200 divided by 50, 50. This is just high school algebra coming to save the day here. And now B is going to be equal to, B should be equal to, when we do this math, should be equal to 40 if I did the math right. 222,000 divide by 5, 0, and that's 40, which is less than 100 button pushes, and it's also even, right? So we always need an even number, because you can't like partially press a button. You can just press a button. So if we ever end up with values here that aren't whole numbers, right, which means we're going to need to work in C#, we're going to need to work in decimals, because we're going to need to be able to hold on to significant digits, and then we're going to need to be able to basically take our value and floor it and see if the raw decimal value is equal to the floored value. Okay, so how does this translate into what we do in code? Well, now, and then you may say, how do we get A? Well, then A is easy to get, because we can just plug the B back into either of these equations that we started with, right? So we can say 94A is going to be plus 22 times 40 equals 8,400. And then you just solve for A. You just do your normal algebraic 22 times 40, 94 plus 880 equals 8,400. And then you'll want to do 94A equals 8,400 minus 880, which is 7520. And then you'll say A equals 7520 divided by 94, which makes A equal to 7520 divide by 94, which is 80. So yeah, 80, right? So now what we need to do is we just need to translate these steps into a formula that we can always use to solve for B, and then we can just arbitrarily decide which of these equations we want to plug B back into, and then solve for A. So, and you can actually kind of reverse your steps here to get to that formula. So let's say formula for B is going to be B equals B equals, and let's actually assign some terms to these things, right? So we can call this we can actually remove these numbers, and we can call this x1 and x2, and this will be y1, and this is y2, and we can call this xt for x total, and call this yt for y total. And the nice thing about doing it this way instead of iterative is that this will work regardless of whatever the numbers are. Whereas if we did it iteratively, if the numbers get really big, we could have some issues, right? So, okay, so where am I? So this got, so yeah, so this, so you can kind of see, we'll just keep substituting our terms here. So this is still, this is x1, this is x, what did I do? All right, that's x2, y2, y. T, this is y, t, this is actually y1, yeah, y1, and this is x1. And then down here, where we start to expand stuff, we just need to replace this and say, this is actually x1. So this value right here is actually x1 times y1. And this value down here is y1 times x1. And we can do the same thing here where we say this is x2, 1, this is y2, and then these right here are the xt times y1. And so we're just kind of working our way backwards. Instead of using hard numbers, we're using variables or terms that we can then just replace with the actual variables from each of these machine inputs. So we'll say yt times x1. So, and then the next thing we did was we solved these. So, or we subtracted them. So this number is going to be equal to, this number is actually equal to two things. It's equal to this guy, this guy. No, I think I turned those. I flipped these around and yeah, because this is 628 is 67 minus, or 67 times 94. 67 times 94. Yeah. So what's on top here is actually it probably doesn't matter. this is actually YT. This is actually XT. This is Y2. This is Y1. X1. This is X2. This is X1. This is Y1. X1, X1. This should be X1. Should be Y. Okay, so then to get down to here, this is where we eliminate these terms right here. These don't matter. Then we look at these guys. And so this number is actually equivalent to YT times X1 minus XT times Y1. And then this one over here is equal to these guys. And finally, we can just get to our final equation, which is going to be this. So, theoretically, if we use this formula, we should be able to plug in just the numbers and get out what we need. So if we were to replace all these values, we've done all the terms right. YT would be 5400 times X1, which is 94, minus XT, which is 8400, times Y1, which is 34, and we divide that by Y2, which is 67, times X1, which is 94, and we subtract that from X2, which is 22, times Y1, which is 34. Now if we redo these, we calculate these out. I promise this is a lot of math, but it's going to save us time. This is 507600, which looks familiar. This is 8400 times 34. That looks familiar too. $67, which is 6298, minus 22 times 34, which is 748. Then we have one more step before we get to the final result. This is going to be 506 0760 minus 285,600. Yep, we're getting to the same numbers, but now we don't have to do a bunch of algebra to move stuff and divide and multiply. Now we just have one equation. We can plug in the machine's values for that and get B every time. So this is going to be 6298 minus 748. So thank you, high school algebra. My high school algebra teacher was Coach Whitney, Jim Whitney. Or actually, was this like middle school? Was this maybe this was algebra one? If that was the case, then my algebra one teacher was. I don't even remember who my algebra one teacher was. My college algebra teacher was Coach Whitney, but let's see. Zero. Yep, 40. Nice. And now that we have that, now we can translate our A formula. So this is going to be, this right here is our formula for B. And then our A formula is going to be, basically it's going to be, let's see, X, no, this is, we're taking our first equation here. So this is our starting point. And then we just need to rearrange stuff. So we're going to solve for A, and we're going to go ahead and replace B. We already know what B is at this point. So let's just assume we know what B is at this point. So then what we need to do is we just need to get everything to one side. So this actually gets minused by that. So it should be A equals, if I can do this in one go, it should be A equals X T minus X2 times B. Then that just gets divided by X1. In which case, that should give us A equals XT, which in this case is 8400 minus X2, which is 22 times B, which in this case is 40, divided by 94, which is X1. So then that's going to become A equals 22 times 40. So that becomes 8400 minus 880 divided by 94. A equals 8400 minus 880, which is 7520, which also looks familiar, divided by 94, and that should get us to 80. Divide by 94. Okay. So this will be our equation to derive number. So this is, so what do I want to say? So this is formula. Formula for A equals this. That. And so then this is all it's going to take for us to solve for the button presses. Now we just need to parse the puzzle input and then do the code to actually solve the thing. So let's get rid of these, because those were just examples to get us to the final. And get rid of these two. Yeah, so this is the nuts and bolts of it. Okay, so let's have a class called machine. Now it's going to have, so each machine is going to have some values which we should be able to substitute for. So um, I'm going to call mine X total public decimal. Uh, and we're going to say a decimal because we want to be able, whenever we have cases where we have not nice round press numbers, we want to be able to have that significance, the decimal points. And if we use an int, it'll always just get rid of that extra. And so we won't be able to detect when partial presses are needed to reach the prize. So this is going to say X total Actually, I don't even think these need to be publicly exposed. So these actually can come in as, so it's private, read-only, decimal. It's going to be called X total. Private, read-only, decimal is going to be X. Call it X1 for lack of a better term. Read-only, decimal, X2. Private, read-only, decimal, Y total. Private, read-only, decimal, Y1. Private, read-only, decimal, Y2. I mean, we could have buttons that have these. We could have a class like a button, and a button has a total, and a button has. Would that make it more difficult to do the? Um, no, but it probably would make it a little bit more descriptive of the actual problem. So let's try that. Why is this not letting me go below? It really did not want me to go down. Let's call this class button. In this case, uh, this actually can be a record, actually. Button, record, button. And it's going to have a decimal, which is basically how much does it move it in the Y and how much does it move in the X. Um, so X movement and then decimal Y movement. And then we have another record which is prize, and that's going to have a, you know what, actually these can probably start off as ints, and when we do the calculation we just need to make sure that we cast it to a decimal. So let's actually start these off as ints. int, int. And this is going to have an x, and this is going to have a y. And then the machine is not going to have these actual private fields. The machines are going to have private read-only button. We'll call this button A, and this will have a private read-only button. This button B. And then this is also going to have a private read-only prize. And then we'll have a private constructor that takes in button, button A, button B, and a prize. And then it will set the fields. That field, and it will set this field. And then we'll have a nice public static method that returns our that creates our machine, and we'll just call it from, and it will be given a string array. Input, and then in here is where we're going to do the logic to split this up. So what do we need to do? We're going to need some regex, but we can basically say, we're just going to say that if input.length is not 3, meaning there's not 3 lines here, we want to throw a new application exception, machine input describing machine is not valid. So that just takes care of the case. If I've done something wrong when I pass my lines to this, I'll know. Otherwise, we know we can say bar button A input equals input 0, bar button B input equals input 1, and bar prize 2. And then we can do some regex to match these things. So bar button A regex is going to equal new regex that looks like basically it looks like this, except here we want a capture group, and it just needs to be and then it's going to want bar button B regex. It's basically the same thing. Here. Price regex equals this guy. I mean, I could just parse this, but I think regex is going to be easier. Like I could definitely split this, like split it, then split it again, then split it some more to get to the final. I need to escape this because plus is a special character, and we actually want the literal. And we just need capture groups here to grab these guys. Which I think that's a capture group, right? Regex, capture group. Yeah, it's just parentheses. Okay, then at this point, what we should be able to do is we should be able to have some validation that says we should have, yeah, we should have some groups, right? So we can say var button a matches equals dot match a regex. Oh, actually, we can say button a regex dot match button a input like that. Oh, we should be able to do the same thing here with B. And then for the prize, we can do this. And then a match, we say if button a matches dot groups dot length or dot count is not 2, or button B matches is not 2, or prize matches dot groups dot count is not 2, then we have a problem. Say throw new application exception, input for button A, button B, or prize is missing. Yeah, let's just do a check for each one. That way, that way there's no guessing. If I mess up this parsing, there's no guessing which one is messed up. So here, you're gonna check for the button A, button B. You're gonna check this guy for the prize. Then I can say throw new application exception, input for button A, missing values. B. And I'm not going to actually test these cases. I'm more putting them here so that it makes my, if I do run into issues, it makes it easier for me to solve. So then we should be able to say var button A equals new button, and we should be able to say int dot parse button A matches dot groups 0. It's not where, oh, groups dot this one. It's going to be parse button a matches dot groups one dot value. We can do the same thing for button B, or button B, and we can do the same thing for the prizes. Prize equals new prize. This is going to be and at the very end, we'll return a new machine that has button A, button B, and a prize. Which I guess this is more like prize location. It's not really the actual prize. It's the location of the prize, but yeah. Let's rename this. Its regex is unused. Oh. Okay, so that's a pretty meaty method for building a machine. So let's go add a test for that, because that could be most definitely wrong. We'll say test, and we're going to have some method data source, method data source attribute. Oops. The data source. Haven't made that yet, but the name of it's going to be from test cases. Public async task from in called with input. It should return expected machine. We just want to make sure we get the parsing right, because that's literally going to be most of the heavy lifting. If the parsing's right, then we just do those equations that we figured out to begin with and move on. So we want to make sure we get this right. So we're going to have a public record of from test case, and that's going to have a string, which is going to be the machine input. And then we are going to have, what are we going to have? We don't, these classes I made, button A, button B, and the prize, they're not public, so I can't use them here. So what I need to do is I need to say expected. They're going to be arrays of ints. So I'm going to say button A expected, button A values. And you may say, well, why don't you just make them public? I don't know. I'm weird about that. I feel like unless there explicitly needs to be public to the outside world, I try to avoid it. Expected button it's going to be expected. Then we'll have a public static method that returns an IEnumerable of func from test case. And it's going to be called from test cases. And the first one it's going to do is called yield return. And it's going to give us new stuff here. So the first input is going to look like this. I wish I was a faster typer. I'm kind of slow. And I apologize. Okay, so that's, and then I'm actually going to change these to be tuples. And I'm going to say int x, int y. Valid? Oh, would be if I remember to put commas in the right places. Okay. Then here we're going to say, okay, the button A should have 94x and 34y. This should have 22x and 67y. This should have 84, 8400, 5400. What we can do up here is we can say from test case, and now, oops, I duplicated that. We can say var machine equals machine dot from test case dot input. And then we'll just assert that we'll say await assert that this machine is equivalent to a new machine. New machine's going to look like, oops, new machine's going to look like this. So I have new button test case dot expected values dot x test case dot expected values dot y. Here, I always get stuck at working in a tiny window. This is going to be, yeah, this is going to be B. It's going to be B. This is actually going to be prize. Expected prize values. Don't need this, and this needs to be an actual prize. Oh, because it doesn't have a. Well, we can fix that. We can say machine from, and we'll just overload. So we'll go back over here and we'll just overload this. Public. Well, actually, let's make this internal. Internal static machine from, and that can have a button, A, button B, location. Oh, say new button A, button B. Just basically calls in this. This static method calls into the private constructor. Now let's build this. And this should give us a good test of if our parsing is working. Nope, it's not. Let's see. Input for button A is missing values. So we know there's something wrong with how we're getting our stuff, so let's just debug this. Debug. There's our string. There's our regex. Now when we match on A, it matched, captures, groups, there's 3 of them. Oh, so the first group is the match, so we actually need to, okay. So we're off by, stop. This actually needs to be 3, 3, 3. And these just need to shift an index. 2, 1, 2, 2. Now let's rerun this. Yeah, awesome. So now we're getting the right machine. And this is complaining because it wants these to use the new regex attribute. So we're going to call this 2 button A regex. So I'm going to want us to do the same thing here. 2 B regex. 2. Ugh, control dot. That's what I want. And this is going to be prize. These can actually just inline these. Rerun this to make sure. Okay, so that's the bulk of our. So then what's going to happen is essentially we are going to here, the first thing we're going to do is we're going to get our machine. So we can say var machines equals input dot split Uh, so let's do read all read all text, and then we can split that text on new lines. So if we look at our input, they're always separated by a line. So if we split by two new lines, we should always get this group of text. So we can say split on environment dot new line that should give us that gives us a string array. But then for each of those we want to then split or select dot split on environment dot new line to list, and then that should give us a list of string arrays. Yep, that's right. And we'll say select machine from to list. Those are our machines now. And then the machines need to solve for their A and B. And actually, that can just be an expression body that basically translates this formula. So we can say private actually this is going to be public decimal number of buttons. Hey guys, don't come out here and be loud. Number of button B presses, which is going to be equal to this. And then we just need to replace these with the actual values. So this will be prize location dot y, and this will be button A dot x. This will be prize location dot x. This will be y1 is button A, so this will be button A dot y movement. This will be B dot. This will be button A dot x movement. This will be B x movement. B okay, what doesn't it like here? possible loss of fraction. Then how do we preserve so let's put this on a line. And we'll just then make a method. So we'll say is it because I'm losing that precision because these are ints? Let me see it. What happens if I change these to decimal? Yeah. Okay. So we're going to work with decimals then. So that shouldn't change anything. We can still parse it with an int. Which means I can actually leave that where it is. And then we can say public decimal number button A presses. That's going to be rise location dot x. And this is going to be button b dot x times number of button B presses divided by we want to divide by x1, which is button A. That's 1, so that's button A dot x. Okay, so that's cool. So let's go back down here. Let's go back to our tests and let's add some more tests. So let's do the whole example here. Make sure we're parsing all the examples right. Yeah. This should be 26, 66. Should be 67, 21. This should be 8, 76, like that. We should have 2 now. Pass. Oh god. This is where Copilot would be, if I was using Copilot, it would be very helpful right now to do some of this mundane test code. Team 6, 84, 7, 7, 8, 7, 0, 6, 4, 0. Yes, 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 yes. 69, 3, 7, 71, 8, 6, 4, 1, 0, 2, 7. Got 4 test cases now, and they all should pass. Great, they do. Now what we should be able to do is should return expected machine. So what we could do is we could just extend this class, and we could just say we could have a bool that says bool expected has solution. And that means that, let's see, the second and the fourth machine. So this guy should be false. this guy should be true. This guy should be true. And the last guy should be false. Then what we could say is we need to have some method that we can say await assert dot that machine the machine is equal to test case dot expected has solution. This should just have a has solution property, and then we can add that just like we did these other methods up here. We can say public bool has solution, which is purely just going to be math.floor number of button presses A equals number of button presses A and math.floor number of B presses Basically, we're just making sure that these things are whole numbers. So then if we rerun our tests, I'm hoping they all pass. Okay. Expected machine solution to have equal to true but found false. Let's see what that's about. These values are all off. Let's see. Yeah, something's screwy with my math. Let's see. Do I need some more parentheses to ensure we're doing the right order of operations? That might be it. Let's see. We should do this first. We should do this first. Let's actually debug one of the steps we had kind of already worked out. So looking at the input 9434. This is the one we know quite a bit about. Debug that. There we go. Okay, let's rerun these because I think maybe, yeah, there we go. We just, yeah, we were doing some, we had some weird order of operations happening that we needed to make sure and be very explicit that these calculations should happen before we divide. Okay, so those all pass, which means which means we need to now we just need a method that calculates the cost. And actually, I think these can probably be private. Then we can just say we need to calculate the cost of the button presses. So A costs 3 tokens and B costs 1 token, and we just add them together. So token, we can say public bool token cost is equal to number of B presses times 1 plus number of A presses times 3. That then what that should mean is up here we should be able to say var result equals machines dot where m has solution dot sum m dot token cost. And then the question is, what is the fewest tokens you would have to spend to win all possible games? Say fewest tokens to win all possible games is our result. Yeah. And as long as I did this part right, which I haven't actually tested, that's the part I need to make sure it does it right. But let's look at our so let's look at, let's say expected decimal expected token cost. Oh, if has solution, then it's that. Otherwise, it's 0. It's false. Expect 0. Oh, which actually means the only thing we really need to expose, we don't even need to expose the has solution. So we could actually say this is private, and then this is public, and then we can, instead of doing that, we can just sum the token cost. And then we can say here, we don't need to assert on the has solution, we can assert on the expected token cost. And then instead of true, we can just put the actual value. So this should be 0. This should be 0. And then the is 280. And this one is 200. 200 for the third machine. And 280 Is it complaining? But now let's rerun these. Okay, so I think we can be pretty confident that part 1 is going to work. So let's do that. .NET run -- project team. It's 13 called claw contraption. Then give it our 13th day's input and see what happens. Hey-o. Okay, now we continue to part 2. Let's get part 2's description. Go down. HTML to mark. Yeah. It's in the description. Get our markdown back. Get over here. Put part 2 in. And we'll clean some stuff up.
I tried everything to lose weight. And then
Goodness, what's that?
This. Try our #1.
It's an ad. Sorry about that. Oh, we also haven't had any music this whole time. Okay, so what's part 2 saying here? As you go to win the first prize, you discover that the claw is nowhere near where you expected it would be, due to a unit conversion error in your measurements. The position of every prize is actually this many times higher on both the X and Y axis. Add how many is this? It's more than 1 million. It's 10 million. So we're off by 10 million. Can decimal, C# decimal, max value can handle way better than you'd think. That's one heck of a range, but not just that. It can go up to 20. Oh yeah, it can definitely handle that. Okay, so that's not a problem. Okay, so this is where they were going to try to screw you because, or not screw you, but this is where they were going to try to trick you, because if you had done this kind of with that iterative approach I talked about, where basically you loop, and so every time you loop, you press a button, and then you increase XY by whatever button you pressed. You at this point, it would work the first time, but at this point, your program would take forever to run, 10 million iterations. So yeah, that's that's why it's kind of necessary to do these systems of equation solution. So I think to make this work, all we need to do is we just need to be able to apply an offset to the prizes. So I don't want to do that. maybe I could just have a just thinking maybe we could just have a width offset or an optional offset parameter here. So we could say this is going to need to be a long offset, and by default it's 0. And then down here when we build our prize, we just say plus offset like that. And then do I need to actually say it's like that. And then we would just say var offset equals is part 2, and if it is, then it's going to have this number as the offset. Otherwise, it's just going to be 0. And actually, I'll make this a little bit just more descriptive. What's this offsetting? Prize location offset. Yeah, so that should handle this case. It will take many more presses than 100. That actually, I didn't even need to check for that. At least not with my input, I didn't. I should probably add that because somebody's input probably has a case that deals with that. So has solution should be, it should actually be and number of A button presses is less than 100 B presses is less than, right? Or is it? It's only possible to win a prize on the second. You estimate that each button need to be pressed no more. So it should be less than or equal to. Okay, and then now we can go back here and say when called with offset, yeah, we can actually say from best case dot offset that, and then it's going to be 0 to begin with. prize location offset. And these are all going to be 0. Then we're going to create 4 new cases. Do have an offset of 10,000. So then this is going to now become hey guys, don't rush slide here. Yeah. So, but the value down here is going to change. So now, now it's only possible to win prize on the 2nd and 4th claw machines. Unfortunately, it will take more than 100 presses. It doesn't even tell me. It doesn't even tell me what these should be. So I guess I'll just set them to 0 for now and then find out what they actually are. Let's test build. We should have a bunch of new cases. Let's run them. And there should be 2 that don't pass. Let's debug this. Oh, down up here. Debug. Prize location. Oh, that's because I've gotta change the offset. It's actually going to be easier just to do it. The value 17. These need to go to, these need to be long something. Continue, it's fine. I don't need to do that. I can just take care of that in the test and say You just take care of that by in the test by saying plus test case dot is location offset. Okay, they all pass, but they shouldn't all be 0. Oh, that's, well, what's probably happening is this check that I added is what do we also need a from here that's like see, we got the input, and then we also have a nullable int that's max presses. In which case, I'm just going to default it to null. Oops. Default to null. That. R presses equals is part 2, and that's going to be 10. It's going to be null. Otherwise, it's going to be 100. It's going to say max presses. Well, that's because this is a nullable int. And here we'll say if private read only nullable int max presses. And then down here, I'll say if max presses as value to thing here. Presses dot value and then this guy's going to have this has become a very bloated test, but so be it. Int max is just going to be null here. Oh. Here it's going to be 100. And what? Holy crap, hold on. How many? That seemed like way more test cases than. Should have 4, right? Should just have 4. 1, 2, 3, 4. I think these are all duplicates somehow. So the very first case is 9434. Those are all duplicate cases. Okay. And then this is going to be test case dot expresses and this actually can just be oh, that's because I'm using I'm using an overloaded version of it's ambiguous. Button, prize location, or button. How's that ambiguous? Oops. Button. Okay. Prize location. Oh. I don't understand what that just did, but debug. What have I done to myself here? I've got myself twisted up. Machine is equivalent to this, to this, to this. Expected machine. So I'm setting that here. Oh, I see what I did. Okay, but that's not right because this one I should be able, on part 2, I should be able to get a solution. It says now it's only possible when on the second and fourth machine. So I should have some value here and some value here. Unit test. Is it because of that check I put in there? I'm going to turn this into check for solution. Private. Private. Full check for solution. So, if this We can say return false if this return false. This is true. And we can return false. One more if. No, this is not as pretty or elegant, but this just helps me think clearer. Personally. Otherwise, we're good. Okay, let's run these tests again. Yes, so now these do have solutions. So I think these are right. So I'm just gonna plug those into their respective test cases. What's the input? That should be these in the order that I declared them. Doesn't really matter because I'll find out if I'm wrong. So this is going to be for the second. This will be for the rerun them. Yeah. Okay. So now let's check against part 2 of our solution. So let's open up our terminal here. I'm really surprised they didn't I'm really surprised that they didn't actually give us the answer to these bigger things to check against, which I'm wondering if that's because they want you to stumble across, they kind of want to force you to use the system of equations approach. And see how like the speed, it took the same time, didn't matter the size of the X and Y location because I'm not iterating, so it doesn't have an impact on the performance. Let's hope this is right. Hey, there we go. 2 hours, right at the 2 hour mark. Okay, so we got both our gold stars for day 13. Let's go back to that puzzle. And since we're here, let's add some tests here that say test public async task from or solution part when input should result. And of course we'll need a private async task that returns a string, and this is going to be called, actually this is going to return this is going to be to return a list of machine. Get basically what this is going to do is what we're doing in our program.main right here. Turn this. say var input equals await file dot read all text path combine. I've written that way too many times, so I really need to. Oh, okay, so maybe I don't want to do that there. Maybe I need to do that. This should be a list of string array. And then here, we'll go ahead and do this part. Say var input equals await get puzzle input var machines equals input dot select, and then these parameters we can just hard code, and we can say 100 and 0. Result equals machines dot sum m goes to m dot token cost. Await assert dot that result is equal to, and this will be a number. Day 13, this 2 is here. We'll do that same thing for part 2. Only now this is going to be some crazy big number. This is going to be null. Isn't it like that? Oh, is it because I can't tell the type? So if I say int offset equals null. Yeah. Say null as a nullable integer. What if I just said max presses null? There we go. Okay, and then that number is going to be something stupid like this. Now when we run our test, they should all still pass. Wonderful. Okay, let's open up our README. Let's show that we did it. But this is actually something different. This is actually clock contraption. This is going to say, yay for algebra. Give this a nice formatting. And we've done day 13. Let's commit it all. Oh, actually, let's pull this into a separate class. Actually, can I don't want this to be a partial. Yeah, I don't really want that to be a partial. Yeah, we can leave it like that. It can be a partial. Let's move it to its own CS file. Namespace is going to be clock contraption. That to its own file. Records kind of look dumb in their own file, but keeps our program CS file nice and tidy. Feature solved. Day 13, part 1 and part 2. Okay, that was a good day. That was straightforward. Unfortunately for me, I can't in there. I need to also go on to do day 14, but I'm gonna do that later today because I've already been doing this for a couple hours now. So I'm gonna bid you farewell till later today. I will see you guys then.